Yo, what's up everyone? Patrick here, and in this video what we're going to do is cover the fundamental concept of numbers. And you may look at this word and think it's fairly general, and you may ask yourself, really, you're going to cover a general concept like numbers? But believe it or not, this could be a little deceiving because there's actually a lot going on in terms of numbers, and there's a lot of different types of numbers, and that's what we're going to go through in this video, the different classifications that numbers can undertake. And so the way I'm going to organize this is initially I'm going to start off with a high-level tree diagram of how numbers can be categorized. And then after that, what I'll do is I'll go through each category in more detail. As the video goes on, I'll explain what each category is, and then I'll provide some examples for each category. Then at the end as well, I'll show different ways that the classifications can be shown, different visual ways that they can be shown. So to start off this high-level diagram here of numbers, now numbers in general, the first way that they can be split up is they can either be real numbers or imaginary. Now most of you at this point have dealt with the concept of real numbers. Perhaps in high school you dealt with concepts like domain and range. So when you're talking about the domain of a function, for example, sometimes you would say x is an element of real numbers. And then you may or may have not covered imaginary numbers, and actually in this video we're not going to focus too much on this. Most of our focus is going to be on the real numbers, but I will describe what imaginary numbers are in general later on. Now, real numbers, they can be broken down into two types. They can either be irrational numbers or rational numbers. And then this rational portion, we split this up. Rational numbers can either be integers, and this can include negative integers or positive integers. It also includes the number 0. I'll go into more detail about that later on. So it could either be integers, or rational numbers can also be, there's no nice word for this here, it's basically any decimals that terminate or repeat a sequence. And again, I'll go into detail of what that means as well. We're just, again, more so writing out the classifications for now. Now, integers, they can be split up into two groups. Integers can either be negative integers, or they can be something called whole numbers. And then whole numbers can be split up into the number 0 or something called natural numbers. And then the natural numbers can further be split up into the number 1, something called prime numbers, or the other possibility is composite numbers. And that's pretty much it right there. That's basically how numbers can be categorized. And so, as I mentioned, notice that most of the categories are under this real category here, right? So all of these numbers are real numbers, and versus imaginary, notice how there's no categories here. So we're not going to talk as much about imaginary numbers, but real numbers we're going to go into more detail. And then, as I mentioned at the end of the video, this is one way to visually show these classifications, and this is actually my preferred way. In my opinion, it just gives you a nice overall view. But at the end of the video, I'll also show you different ways that this could be shown, especially this row right here, from real rational integers, whole numbers, and then natural numbers. There's a popular way that this portion can be shown, and I'll show it to you at the end of the video. So let's start off with those two high-level classifications for numbers, so real versus imaginary. Now, real numbers, the way I like to personally think of them, is basically any number that is between negative infinity and positive infinity. Right? So most numbers, basically, you've been dealing with throughout your school career have been real numbers. So any numbers from negative infinity to positive infinity. So any integers, the number 0, any kind of decimal, whether that decimal terminates, meaning like 0.35, it terminates there at the 5, or if it's a decimal that repeats, so for example like 1/3, which is 0.333, like that, or let's say the number pi, 3.14, etc., keeps going on, that decimal expansion forever. All of these kinds of numbers between negative infinity and positive infinity are real numbers. Now, imaginary numbers, you may find different definitions for this. The way I like to think of it is it's something called a complex number that is written in terms of something called an imaginary unit, which is usually shown as the letter I. So a complex number that is written in terms of I, and what that I is, it's basically the square root of -1. And so usually it's going to be written as some kind of real number, which would come from here, times that imaginary unit I. So for example, like the square root of -9. We can take this square root of -9, split it up into the square root of 9 times the square root of -1. And then what's the square root of 9? It's plus or minus 3. And then the square root of -1 is I. So the square root of -9 will be plus or minus 3i. I know it's kind of weird, and as I mentioned, we're not going to be focusing too much on this in this video, but believe it or not, there's actually a lot of important real-world uses for imaginary numbers in physics, geometry, engineering. It takes a lot of complex calculations and helps solve them in a more easy way, right? So as weird as this all sounds to you, especially if you've never heard of it or if you've never been exposed to it before, there is actually a lot of real world uses for imaginary numbers. But again, we're going to be focusing more on real numbers. Now, the next classification from real numbers, remember we said real numbers can be either irrational or rational numbers. And I'm going to start off with talking about rational numbers. I'm going to actually erase this here and give myself some room. So you can have this, that whole diagram that we had at the beginning of the video on one page, and then maybe the next couple of pages you could take each category, and whatever I'm writing you could write under each category as a list. So rational numbers, they're basically numbers that can be written as m over n, a fraction where m and n are integers. However, there's a restriction here, n can't be 0. Right? You can't be dividing by 0. It would be undefined there. So m and n are integers. M can be 0, but n can't be. So you can have like 0 over any number here, let's say 5, that would give you 0. And 0 is a number, and it's actually a rational number, because 0 can be written as 0 over 5 or 0 over any number besides 0. But something like 5 over 0, this would be undefined. Right? So that wouldn't fall into this category. So that's why there's that restriction for n. So there's a lot of numbers that could be. There's actually an infinite amount. So notice that any integer, so for example, the integer 2, it could be written as a fraction of other integers. So this could be written as a fraction 2 over 1, or it could be 4 over 2, or it could be negative 24 over negative 12, right? When I say integers here, I mean any positive or negative integers. So because 2 can be written in this format, it's a rational number. Now, a rational number doesn't necessarily have to be an integer. It could also be decimal. So like the decimal, for example, 1.4, we can take this and write it in that format. We could take 1.4 and write it as 7 over 5. Or we can write it as 14 over 10. Or negative 7 over negative 5, or negative 14 over negative 10, or 28 over 20, right? This decimal can be written in that format as a fraction of integers, and so 1.4 is going to be a rational number. And then even numbers that are decimal numbers that repeat, so for example, like 1 over 3, as I mentioned before, 0.33 repeating, well, this can be written as a fraction of integers, 1 over 3. So that would be a rational number as well, right? So a rational number is basically any number that can be written as a fraction of integers where that denominator can't be 0. Now, before getting into the irrational numbers, I actually want to go into detail with the rational portion in the next classifications, and then I'll go into the irrational. I feel like it's going to be easier to explain then. Now, rational numbers, as we showed in that high-level diagram, can either be integers or it could be decimals that terminate or repeat a sequence. So let's start off with what integers means. Now integers, it includes the number 0, and then it's basically plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, etc., etc. Another way this could be maybe shown is you could have 0 in the middle, and then you have 1, 2, 3, etc., etc. And then going the other way, you have negative 1, negative 2, negative 3, etc., etc. Right? So that's what integers are. Now, the other type of rational number are decimals that terminate or repeat a sequence. So a decimal that terminates, for example, like 1.2, right? It's terminating there. There's no other decimals after this here. And 1.2, it's rational because it could be written as 6 over 5, or 12 over 10, or negative 120 over negative 100, right? Any decimal that terminates can be written in this format as a fraction of integers. Also, any decimal that repeats a sequence can be written in that format as well. We went over 1 over 3, right? That would be 0.333. Just repeats a sequence forever. And the sequence doesn't necessarily have to be the same number. It could be multiple terms. So for example, like 1 over 11, if you plug that into your calculator, you would get 0.090909, and then that sequence repeats. So notice that that sequence is 2 terms. And you can have more than 2 terms that are repeating. So basically any decimal that repeats a certain sequence until infinity can be written in that format as a fraction, m over n. right? And then as we know, any integer can be written in that format as well. You could just take the integer and then put it over 1, right? The n value can be 1. 1 is an integer. And then 0, the m can be 0, and then the n can be any other number, any other integer besides 0, and you would get 0. Right? So any integer, any decimal that terminates or repeats a sequence is a rational number, meaning it could be written in that format, m over n. Now, irrational numbers, knowing all of this here, it's basically the opposite. So irrational numbers can't be written as a fraction of integers. All right, so it can't be written as m over n. And more specifically, irrational numbers, they're basically decimals that don't terminate and don't repeat a sequence. Right, so here these decimals either can terminate or repeat a sequence, one or the other. But here, irrational numbers, they're decimals that don't terminate and don't repeat a sequence. So for example, 1 over 3, notice that this doesn't terminate, but it repeats a sequence, so it can't be an irrational number. So examples of this would be like the value pi. Pi, 3.14, etc., the decimal expansion, it never terminates and it doesn't repeat any sort of sequence. Same with Euler's number, E. Another popular example of irrational numbers is the square root of any non-perfect square integer. Non-perfect square integer. So for example, like the square root of 2 or the square root of 3. Notice the square root of 4 wouldn't fit under this because that's a perfect square. Square root of 4 would be plus or minus 2, which would be an integer, which would be a rational number. But square root of 2, square root of 3, square root of 5, square root of 6, any square root of a non-perfect square integer is going to be an irrational number. It's going to give you a decimal that doesn't terminate and doesn't repeat a sequence. In fact, the nth root doesn't have to just be a square root, but the nth root of any integer, there's only 2 results that could come about. It's either going to give you an integer, which is going to be a rational number, or it's going to give you an irrational number. Those are the only 2 possibilities. So for example, like the third root of 8, notice that that would be 2. Or the third root of negative 8 would be negative 2. Both of these would be integers, rational numbers. But for example, like the third root of 7, notice the third root of 7 won't give you an integer, so this would be an irrational number. Right? So the nth root of any integer, any positive integer, if this is odd, then this could be a negative integer as well. I'll just leave it as integer for now. This result here either is an integer, but if it's not an integer, then it's an irrational number. All right, so irrational numbers, the descriptions aren't as nice, in my opinion, as rational number, but what you want to remember, it basically can't be written as a fraction of integers, m over n, and it's basically any decimal that doesn't terminate and doesn't repeat a sequence. So then continuing on with the classifications from that high-level diagram, we're now going to go into more detail with the integers. And as we talked about, integers, they're split up into negative integers This one's pretty simple. Basically, all the negative numbers there. So -1, -2, -3, etc., etc. Or the other category integers can be split up into is something called whole numbers. So if we took this and from it took out the negative integers, what would be left? Well, we'd have 0, which is a whole number, and then all the positive integers, like 1, 2. You know what? Actually, I'll write it over here beside it. So 0, 1, 2, 3, etc., etc., like that. Now, whole numbers can further be split up into that number 0 by itself, or something called natural numbers. And so from here, we took out the 0. What's left? All of the positive integers. So 1, 2, 3, 4, etc., etc. That's what natural numbers are. Now, some sources may include 0 as a natural number. Most won't. And I'm assuming in this video that 0 is a whole number, but it's not a natural number, right? So it has its own category under whole numbers over here. And then natural numbers, basically positive integers, are split up either into 1, the number 1, and then the rest of the numbers can be split up into either prime numbers or composite numbers. Okay, and prime numbers are basically numbers that only have factors of 1 and itself. Kind of running out of room here. So some examples of prime numbers. There's an infinite amount. But prime numbers would include 2, for example. What are the factors of 2? It's only 1 and itself. 3 is also a prime number. What are the factors of 3? 1 and itself, 3. Now what about 4? Is 4 a prime number? Well, what are the factors of 4? It's 1, 2, and itself. So notice there's another factor other than 1 and itself. So 4 is not a prime number. 5 would be a prime number because the only factors are 1 and 5. 6 has 1, 2, 3, and 6. So the 2 and 3, those are factors other than 1 in itself. So 6 wouldn't be a prime number. Right? So natural numbers, either 1 isn't a prime number or a composite number. Right? So natural numbers, either 1 or they're prime numbers, numbers that only have factors of 1 and itself. So 2, 3, 5. The next one would be 7. The one after that would be 11. Or they could be composite numbers, and I'll just write the definition over here. Composite numbers are basically natural numbers. I could have maybe even wrote here natural numbers or positive integers that only have factors of 1 in itself, but composite numbers are basically natural numbers. So a positive integer that has factors other than 1 and itself. Okay, so 4, for example, is a composite number because the factors are 1, 2, and 4. 6 is a composite number, 1, 2, 3, and 6. The next composite number would be 8, right? 1, 2, 4, and 8. 9 would be a composite number. 1, 3, and 9. 10 would be a composite number, right? So natural numbers, 3 different categories. Either it's just 1, prime numbers, or composite numbers. And that's pretty much it for all of the classifications and their specific definitions and examples. One thing I want to mention, as I mentioned at the beginning of the video, is I actually want to go over this portion here. Sometimes you'll see this portion represented in a certain way. So what they'll do is they'll draw like a big circle like this, and then they'll say within this big circle here is all of the real numbers. And then within real numbers are rational numbers. So they'll draw another circle like this. It's not the best drawing, but I'll try my best here. So within that will be rational numbers. And then within rational numbers are integers, so that would be another circle. So we would have integers. And then within integers, we have whole numbers, so that would be another circle. Whole number, whole numbers. And then within whole numbers, we have natural numbers like that. So that's another example you'll see of taking this area here and then representing it. Personally, I prefer the first diagram that we had because it shows all the other combinations as well. Notice here we don't have irrational numbers. It's hard to see where everything kind of fits in, like the irrational numbers, or it's hard to see where the decimals that terminate or repeat a sequence, which is a type of rational number, that's not going to be within here as well. But they just take this area sometimes and show it visually with these circles. So a potential question that could come up with these circles is they can give you a list of numbers. Notice all of these are real numbers, so they're going to fit within this big circle somewhere. And they'll give you a list like this, and they'll ask you to put it in the correct place. And so the way you want to do that, so for example, if we start with pi, you want to take the number, and then you want to start off with the smallest circle and then move your way out. So we take pi. Is that a natural number? No, it's not a natural number. So then we move out to the next category. Is it a whole number? No, it's not a whole number. Is it an integer? No, it's not an integer. Is it a rational number? No, pi is an irrational number. So it's going to be on the outside here. It's a real number, but it's irrational. So it's in this area. It's not within the rational area here. So we would put pi right there. And that's how you want to deal with all of these numbers. So -4, is it a natural number? No. Is it a whole number? No. Whole numbers, remember, they're 0 and positive integers. -4 is a negative integer, so it's a type of integer, but it's not a whole number, so -4 would go in that area right there. It's a type of integer, but it's not a whole number. So it would go in between right there. Right? What about 4/3? Is it a natural number? No. Whole number? No. Integer? No. Is it a rational number? Yes. Because 4/3, by the way, it's not an integer because 4/3, just because you get a fraction doesn't mean it can't be an integer. 4/3 is 1.33 repeating. Right? So it's not an integer. But for example, if this was like 4/2, then this would equal 2, and then that would go under the integers. Actually, in fact, 2 would go under the natural numbers. So be careful, these types of questions, you can get a fraction that simplifies to something else. But 4/3 doesn't simplify, It is a decimal that repeats a sequence, so it's not an integer, but it is a rational number. It could be written as a fraction of integers. So 4/3 would go in that category. What about 0? Is it a natural number? No. Is it a whole number? Yes, it is. 0 is a type of whole number. So we're done with that. 5, that's a positive integer. That's a type of natural number, so that would go within there. What about 1? 1 is a type of natural number. Right? It's a positive integer, so it would go within there. √3, notice, remember, square root of any number and nth root of any number is either going to give you an integer or it's going to give you an irrational number. And notice that √3, it's not going to give you an integer, so it's an irrational number. So we move out, it's not rational. It is a real number, but it's not rational, so it would go over here in that area. What about the 4th root of 16? The 4th root of 16 is 2, which is a positive integer. It's actually a natural number. So, and you wouldn't actually write 2 there. You'd actually write that same format, 4th root of 16 would be a natural number. And then 2.45, is it a natural number? No. Whole number? No. Integer? No. But it is a rational number. It is a decimal that terminates, that stops. So 2.45 would be a rational number. It would go over here. Right? 2.45 can be written as 245 over 100. Right? A fraction of integers. So if you do get a question like this, popular type of question where you're given this diagram and then they give you a list of numbers, then you got to put the numbers correctly in the diagram. Always start off with that inner circle and then just move your way out, and then whenever you find that number being in that classification, that's where you write it, as close to that border as possible. And that's pretty much it for numbers and their classification.